Hi, this is Dave Johnson with another edition of Math Off Topics. Today I want to do the integral of sine x using a Riemann sum. And in the previous video, I did the integral of cosine x. And the way I did that was by using the Lagrange trigonometric identity for the sum of a cosine series. Here I'm going to use the analogous Lagrange's trigonometric identity for the sum of the sine series. I've made videos on these other topics, and so I will provide the links to those videos in show notes below. So let's get into it. Now, I've taken the liberty of writing a few things down just to save a little bit of time, but here's the integral that we want to do today. So this integral of sine x, and we're going to do this from 0 to b, but of course, I'm going to show you how to generalize that to the integral from a to b of sine x dx. And of course, anybody can do this integral using an antiderivative. You learn that first thing when you do integration in a calculus course. The problem is, and this actually makes the problem a little bit more fun, more challenging, is can you do it using the limit of a Riemann sum? And so let's remember, when you have a definite integral of this type, you have it's the limit as n goes to infinity of the sum as k goes from 1 to n of whatever the function is. So in this case, sine of x sub k, k being the index here, times your delta x. And we remember that we define delta x when we can say that the delta x's are constant, which we do at this level. Delta x is equal to b minus a divided by n. And since we're taking a to be 0, this is just a simplification. So b minus a over n becomes b over n. Likewise, x sub k is a plus k times delta x. And again, since a is 0, we get x sub k is equal to k times b divided by n. Now I've written down here, this is Lagrange's trigonometric identity for the sine series. And being able to sum this series, it's not difficult, but it takes a little bit of effort. And once you have it summed as a single expression like this, then it makes it a lot easier to do this limit. So what I'd like to do is I always like to have a handle for my integrals. So let's call our integral I, and let's go ahead and substitute in. So I is equal to limit as n goes to infinity of the summation as k goes from 1 to n of sine of, now x sub k is, as we said before, k times b over n. So k times b over n. And then times your delta x, so times b over n. And basically the rest of this exercise is to sum the series and then take the limit. So let's go ahead and I'm going to write this as limit as n goes to infinity. And I'm going to bring the b over n out. So b divided by n times the summation. K goes from 1 to n, or from 1 to n of sine of kb over n. Now, if we look at the our series, our Lagrange series, and do a little pattern matching here. So k times theta is the same as k times b over n. So if we let theta equal b over n, then we can just go ahead and substitute directly into our closed form expression for the sum. So we get limit as n goes to infinity, b over n times, now the sum is going to be written using this expression. So let me go ahead and just substitute. So cosine 1/2 theta, so I can write that as b over 2n, because theta is b over n, minus cosine of n plus 1/2 times theta, which is b over n. And that's all in the argument to the cosine. And then divide by 2 times sine 1/2 theta, which is b over 2n. Close parenthesis. Now we need to start to simplify and take the limit. So limit as n goes to infinity. And what I want to do is, just to simplify matters a little bit, I want to bring this 2 out, and notice this b over 2n, and I want to make this b over 2n, and it's going to all be in the numerator. If you think about how this is going to work, and then I'm going to bring that b over 2n down below underneath here. So let me do that. I think I can do that in one step. So this becomes cosine of b over 2n minus cosine of, and let's go ahead and distribute the b over n in the second cosine argument. So we get these n's will cancel, and we get b. So we get a b here, plus, and then the b over 2n, write it that way. and now, remembering that we still have this b over 2n, that's this 2 here comes out here, and then we've got a b over 2n, and I'm going to write that in the denominator of this. So I can write this as sine b over 2n divided by b over 2n. And I think now most of you can see where this is going, because what we want to recognize is that the limit as n goes to infinity of this, well, this is sine 0 over 0, or the limit is this thing goes to 0 divided by this thing goes to 0. Well, this limit here down below is going to be 1, and this is going to become 0 because n is going to infinity, and this is going to become 0. So I can go ahead and maybe indicate that. And all of this is going to go to 1. And so we end up with, I've already taken the limit, so we get cosine of 0, which is 1, minus cosine b divided by 1. So that's the first part, because what I wanted to do was figure out what this integral was. But what we really want is the integral from a to b, where a is not necessarily 0. So let me do that next. So the integral from a to b of sine x dx is equal to, we'll do it this way, the integral from a to 0 of sine x dx plus the integral from 0 to b of sine x dx. But I can rewrite this if I swap the limits here, make it 0 to a instead of a to 0, put a negative sign, and let's go ahead and write this term after this term. So rewrite it as the integral from 0 to b of sine x dx minus the integral from 0 to a of sine x dx. And of course, this is going to be, as we've found right here, the integral from 0 to b gives you 1 minus cosine b. So let me write that. So 1 minus cosine b, and then minus the quantity 1 minus cosine a, because there's really no difference between a and b except their value here. So write this as an a, and then simplify. So the ones cancel, and you get cosine a minus cosine b. And this is exactly the answer that you would get if you did this using an antiderivative. So see if I can pull all this in together so you can see it. So hope you found that helpful. I hope you enjoyed it. If so, please like and subscribe, and I will see you in the next video.